Well, I'm sorry I'm not there with you in Lisbon. I suspect some of you were in Corfu last year, so I got to see those of you who were there then. I hope you're enjoying Lisbon. And so I'm going to give a talk. I'm going to briefly review local measurements of the Hubble constant, and then I'm going to go through frequently asked questions, things that come up a lot that you may wonder about, or you may have your own questions you can ask at the end. And I'm at the end of going over the questions, I'm going to talk a little bit about new data coming in from the James Webb Space Telescope. So I think probably this needs no introduction to this group, but why are we pursuing a precise measurement of the Hubble constant? And I think the reason is probably obvious to most people, that this is one of the few things you can check all the way from the early universe to the late universe. So it's sort of an end-to-end test for lambda CDM. You can predict, of course, the value of the Hubble constant. The cosmological model predicts the angular scale of fluctuations shortly after the Big Bang. You can observe those fluctuations, and you can use that comparison to set the 6 free parameters of lambda CDM. Then you can use lambda CDM once calibrated to predict the whole expansion history of the universe, H of Z. That leads to a very precise prediction of the Hubble constant. And so a strong test of this is to measure it locally and directly using the kinds of tools I'm going to talk about. So we started a project more than 15 years ago now to reach a percent level measurement of the local value of the Hubble constant, leveraging primarily the Hubble Space Telescope, but now also the James Webb Space Telescope. So this is a Generation 2 project with the Hubble Space Telescope based on 20 competed proposals, now totaling more than 1,000 orbits. So this is quite a large investment. And our route to measuring the Hubble constant is totally empirical, and it's a 3-rung distance ladder of the best tools that we have today, geometry to calibrate Cepheid variables, and then type 1a supernovae. So key elements of SHOES that differentiate it from previous efforts to measure the Hubble constant. A key element is to make the measurements of Cepheids on rung 1 and 2 with the Hubble Space Telescope, which cancels flux calibration errors that were a big issue in the past. We make our measurements in the near infrared to minimize the impact of dust. Past measurements had been in the optical. We use the best available supernova data. That was not always the case in the past. People could not observe Cepheids out as far with early instruments, and so they would calibrate things from photographic plates from the 1930s. Our data is based on the Pantheon Plus, and I think Dylan Brown is going to talk more about Pantheon Plus later. We do a very comprehensive error analysis. We keep track of covariance between data and model, and we do a lot of variance of the analysis, particularly if anybody has ideas of other ways to do the analysis. They can either grab the data themselves, so that's the last point here, is we publicly release the data, 10 to the 7 data numbers, and the code to load it and run chains, and that's on the website that I had on the title slide. I'll flash it up again later. Okay, so I'm going to give you a brief overview of the current version of the SHOES distance ladder. So there are 3 independent geometric ways we can calibrate Cepheid variables. There are parallaxes in the Milky Way, and that can be done 3 different ways, which I'll briefly review. Second method, detached eclipsing binary systems in the Large Magellanic Cloud. These are stars orbiting other stars, and you can time the eclipses. You can measure the Doppler velocity to turn that into a linear distance. And by comparing that to surface brightness of the stars, which is calibrated with interferometry, this becomes a geometric distance. And then the third method is water masers observed in the radio in tight Keplerian motion around a supermassive black hole in the galaxy NGC 4258. This is a very special galaxy because it's the one that is edge on in its circumnuclear disk, and so it gives this sort of optimal setup. This has been tracked for 15 years, and each of these methods is good now to about in the first case, 1%, 1.3%, and 1.5%. The most important thing to me is that these are independent. They literally have no measurements or concepts really in common. And so that's a powerful way to start out the distance ladder. Okay, so let me just briefly talk about parallax, because I think there's been the most developments on this side in the last couple of years. And I know Richard Anderson is going to talk a little bit about this later as well. In order to measure useful parallaxes to calibrate Cepheids, which tend to be a few kiloparsecs away, you really need parallaxes that are better than about 40 micro arc seconds. And so that's why there have been new developments, because this has only been possible really in the last 10 years or so. So the first approach we developed ourselves was to use the Hubble Space Telescope in spatial scanning mode that was developed to measure high precision astrometry, to measure high precision parallaxes. And so we did that for about 8 long period Milky Way Cepheids. This was good enough to calibrate the Hubble constant to about 3%. Also important is you can measure the fluxes of the Cepheids with the spatial scan data, so that the Cepheids are measured with the same telescope as we'll get to for rung 2. Approach 2, which is now greatly surpassed approach 1, is to measure the measure the photometry of the Cepheids with the Hubble Space Telescope, but to get the parallaxes of the Cepheids from Gaia, most recently from Gaia Data Release 3. And so this gets to about a 1% calibration of the Hubble constant. And then a third approach, more recent, is to look at Cepheids in open clusters. And Richard, I know, will say more about this, but there's about 17 Cepheids that have been observed in open clusters in the Milky Way. The advantage here is, rather than be limited to the parallax measurement from Gaia of the Cepheid, you can average over hundreds or even maybe many thousand parallaxes of stars in the clusters. And so that reduces the errors further just by averaging down to about 10 micro arc seconds. And this also gets to about a 1% calibration. And so if you combine these 3 different ways, this is the basis based on parallax of calibrating the Milky Way Cepheid period luminosity relationship. Again, just to remind you, all of the Cepheids in this case, the 3 generations from the blue, which was the first effort, gray, the field stars, and red, the cluster Cepheids, are all on the HST photometric system. And by the time Gaia reaches its final data release 5, I think in a few years, this step alone will be good to about 0.4%. So there's more to come in the future. Okay, just to briefly review the other ways of calibrating Cepheids, we have, as I said, the detached eclipsing binary distance to the Large Magellanic Cloud. We've gone back and observed Cepheids in the Large Magellanic Cloud with the Hubble Space Telescope. This really shows you the power of near-infrared observations. As you climb up this diagram from bottom to top, you go from the visible to the near-infrared or the de-reddened near-infrared to get very tight period luminosity relation. And then the third calibrator is HST 4258. The advantage here is it's a big metal-rich spiral, just like the Milky Way and supernova hosts. We've gone back and observed more Cepheids in this galaxy in the last year and a half to double the sample there. We now have over 600 Cepheids there. Okay, so rung 2, we're now up to 42 Type 1a supernovae in 37 hosts observed with the Hubble Space Telescope. This is where most of the HST time goes. There's a good Type 1a supernova within range of Cepheids about once a year. And so to collect these 42 have taken sort of the last 40 years of supernova yield. What that also means is it's unlikely we will double this sample in the lifetime of Hubble. So this is sort of the best that we're likely to get from this. We've reprocessed all the data using an improved pipeline and new STSCI reference files. So these are the Cepheids, the composite light curves observed in each of the host galaxies, where they're observed in 3 filters. The light curves shown here are used to identify that these are Cepheid variables and to determine their period. And then we observe in 3 filters, near-infrared, 2 optical filters, to measure a reddening or dust-free distance measurement to each of the galaxies with their period luminosity relationships that you see here on the right. And then the third rung, which Dylan Brout will talk more about later, is the use of type 1a supernovae in the Hubble flow. We don't do this too nearby because we want to avoid local flows. We don't want to do this at too high a redshift because the value of the Hubble constant changes and you'd have to account for that. And we want to make this as simple as possible. So we use a kind of intermediate range, 300 type 1a supernovae that all live in spiral hosts so that the host type is just like the hosts on the second rung. So we have matched those as well. And for a full overview of the third rung, please take a look at the Pantheon Plus sample recently published. Skolnick-Brout supernova covariance has now been modeled, and the data is all public. Okay, so you combine these three. This is a visual for it, but we are actually simultaneously fitting 5 global free parameters: the luminosity of type 1a supernovae and Cepheids, the slope of the Cepheid period luminosity relationship, the dependence between Cepheid luminosity and metallicity, and 5 log H naught. We now have a non-diagonal covariance matrix where we've characterized the covariance between Cepheid and supernova measurements. It's a linear set of equations, so it's not necessary to do an MC-MC, but it's nice to see the relationship between parameters. Okay, so I think you're probably familiar with the result, but it's 73 plus or minus 1. This nominally includes systematics, what people in the past would have called systematics, because we've formally put them into the covariance matrix. And this is 5 sigma different from Planck, or if you include the cluster Cepheids, which is more recent work just in the last year, then you're at 5.3 sigma. And here are samples from the chains. Our baseline result in green here with 100 million samples really is at or now beyond 5 sigma. The chi-square is very good for the results, and that is based on errors which are determined not from the model but from the data, and so that's a pretty strong statement. We've done 12 categories of variance of the analysis, 67 variants in all. Some of these are bifurcations of the data set. So you split the data set in half and look at, the most crowded half versus the least crowded half, or, this supernova survey versus that supernova survey. So necessarily, you have different precision for a test than you actually have the Hubble constant tension. I'll say more about that later. Here are some of the most interesting variants that people have considered. For example, I'll just draw out this one. People have speculated that we could live in a local void out to redshift to 0.05, so we could start the Hubble flow at 0.06, and it makes little difference. The sort of bottom line here is that it's been hard for us to see any results that are much below 72.5 or much above 73.5, and we propagate the scatter that you see in these variants as extra systematic. Of course, it's not just us. As you're familiar with the Hubble tension, there are other methods. Ours is the most precise, primarily because in the case of supernovae, we have more supernovae, more calibrators. In the case of our Cepheid calibrations, we have more independent calibration sources like parallax. But there are other techniques one can use. They're consistently coming out above the local, the Planck measurement. There's no really precise measurements of the local value of the Hubble constant that are lower than the Planck measurement. So this is the essence of what we call the Hubble tension, which I think is quite interesting. Okay, so that was an overview, got through pretty quick. Now I'm going to go through questions or issues or whatnot that either have come up recently or have come up in the past or might be on your mind. And so in no particular order, one question we've been asked or people can be concerned about is how reliable is the photometry of the Cepheids that we observe, particularly in the presence of backgrounds, which can be either dense, like you see in the red area. This is the inner region, for example, of NGC 4258, or in the less dense areas, the outer region shown here in blue. So we've done 6 validation tests of our backgrounds or crowding. This is covered in section 7.1 of our paper. Here is just one of those 7 or 6 that I think is very visual, which is basically, as I said, that you can observe Cepheids in the same galaxy, which they all have the same distance to us from us in either where the backgrounds are dense or the backgrounds are relatively empty. Now, we estimate the backgrounds by throwing down fake stars, what are called artificial stars, into the images at known brightness. Then we recover them so that we can measure the background. Now, because this process is not a systematic, it's statistical, and it is only a source of noise. In principle, there should be no disagreement between the distance measured from a dense field or a relatively empty field like this outer field. And indeed, that is what we see. Shown here on the bottom is in blue, Cepheids in the outer region, and in red are from the inner region, and the distances or 0 points agree to about 2/100ths of a magnitude. Now, independent of all the checks we've done, there's another group, the Arakaria group, that reported, I guess about 2 years ago, that they went back to the original pixels with HST and made their own measurements using different techniques to observe the Cepheids, and they got consistent results. So I think using best practices, this is sort of what the data gives. What I think of as the strongest test of our background estimate is this diagram, where we can look at the residuals from the distance ladder for the Cepheids as a function of the local background. Now, the local background is just a measurement from artificial stars. It's not part of the model. And so the way to get rid of the Hubble tension would be either for the Cepheids and supernova hosts, that is rung 2, for you to be underestimating, sorry, let me get this right. For you to be, yes, underestimating the background, so that the Cepheids shown here in the Cepheid bins shown here as red points would follow this red dash line. Or alternatively, you could be overestimating the background of the Cepheids in rung 1. So that would be, for example, NGC 4258. So the points in black show you those Cepheid residuals versus the trend to solve the Hubble tension for those points would be the dashed black line. So this is a null test, and in this case, the data passes the null test. The data is consistent with 0 residual, and it's strongly inconsistent at more than 8 sigma for this test of on average 2/10ths of a magnitude over or underestimate of the background, depending on whether the Cepheids come from rung 1 or rung 2. Now, I wanted to mention another test. This is I mention it because there was a paper recently that revisited this test. And so this test is looking at the amplitudes of the Cepheids observed in distant galaxies. Now, the near infrared background levels are much higher than in the visible. And so this test is most powerful when you do it in the near infrared. That's where the amplitudes will be compressed by background. What do I mean? Well, if you have a variable object, it has a certain amplitude. If you add that variable object to a static flux object, then the combination will have a smaller amplitude because the static object has no amplitude. So you're looking at the average of the two. And so you can compare the amplitudes in different regions as an alternative way to estimate the background. So in the regions where the background is very light, like you see here, you'll have a full amplitude for the near infrared light curve shown here in red. In the cases where it's moderate background like this, you'll have a compressed amplitude. In the case where the background is very, very heavy, and we don't even use Cepheids this in regions this dense, but it's still useful for this test, you could completely compress the background like you see here. So you could compare the apparent amplitude to the expected or uncompressed amplitude seen in the Milky Way, and this provides an estimate of the background. And so the question here in this test, do the backgrounds estimated from the amplitudes match what you get in artificial star measurements? Is the delta between those 0? Now, we only have this near infrared amplitude data for about 10% of our hosts. So this is necessarily a weaker test than some of the other tests I described. We presented this test in a 2020 publication where we found a delta of minus 0.029 plus or minus 0.039. So yes, it was consistent with 0. It passed this test. There was a recent paper by Sharon Kushner and our group that reanalyzed this, now having additional information about amplitude data in the Milky Way. The result, the test is even a little bit closer to 0, but the error is a little bit larger. And so the backgrounds pass this test in either case. To be clear, this test alone would be 3 sigma from a delta of plus 0.2 that you would need to match Planck. But to be very clear, 3 sigma is not the significance of the H naught tension. It is just of this test of this specific error for which there's no evidence for this error, and you would still have to combine the 6 other tests to see what the total combination of evidence against this particular source of error is. I'm belaboring this point, but I understood that somebody had asked me to go over this. So just to give you sort of maybe a useful analogy, I could do a test whether the supernovae that appeared to us on one day of the week, Tuesdays, were consistent with the ones we saw on the other 6 days of the week. And so if I measured no difference between Tuesday and the other days, I would say I passed that test. Now, the error bar on Tuesdays would be necessarily bigger because I don't have as much data on Tuesday as I have for the other days. That is not the significance of the tension. That is the significance of a test which bifurcates the data. Okay, another question that people often ask is, are these different anchors that I described, do they give consistent results? So we can use any 2 anchors to predict the third. They are consistent within 1 sigma. They give slightly different values for the Hubble constant, anywhere from 72.5 for NGC 4258 to 73.5 for the LMC, and Milky Way parallaxes are in between. Okay, is the H naught you get from Cepheids and tip of the red giant branch consistent? So I think Richard Anderson may talk about this a little bit later on, but I'll say something about this because I've done some work on this most recently with the CATS collaboration. So the simple answer is it's not so simple, and the reason is because Cepheids or tip of the red giant branch do not directly measure H naught. There are other steps involved. They are only a kind of middle tier. And the other thing that makes this a little more complicated to answer is there's been growing evidence that I think is now pretty definitive that tip of the red giant branch is not a perfect standard candle. It has variations at the 10th of a magnitude level. Again, I think Richard is going to show some evidence of that. But the key thing here is it doesn't matter if it's not a perfect standard candle. The key is you really need to match the luminosity of it between the rungs. And so we started a project about a year ago, the CATS group, which you can see the folks below who have worked on various teams, because we realized that tip of the red giant branch is actually quite difficult to measure because it uses something called edge detection, which is sort of like taking the derivative of some noisy data like you see there on the right. And so we thought a good way to train the method for doing this is to use measurements of tip of the red giant branch in multiple fields around the same galaxy. And so one can optimize the algorithm for measuring tip of the red giant branch to minimize the dispersion of multiple pointings around the same galaxy. One of the things we discovered is that not only is tip of the red giant branch not a perfect standard candle, we found a way to standardize it. We found that there was a dependence of the luminosity of the tip of the red giant branch on what we call the contrast ratio right near the tip. That is the ratio of stars just above the tip to below the tip. The stronger, higher that contrast, the more luminous the tip of the red giant branch is. We see this at about 5 sigma confidence in the ghost galaxies shown here in the Large Magellanic Cloud, different pointings there, and in NGC 4258. And so we then proceeded to measure the Hubble constant using a 3-rung distance ladder connected to supernovae, but using this contrast tip relation to standardize the TRGB across the distance ladder. And this is published recently in Skolnick et al., or shown here. We get 73.2 plus or minus 2.1, so it's quite consistent with the results I previously presented from Shoes. But this is a breakdown of where the difference comes in the Hubble constant between this analysis, the one from the CCHP, and the one from the EDD group. And interestingly, and to our didn't necessarily know this going in, the biggest difference we see in the Hubble constant from these analyses are not from tip of the red giant branch versus Cepheids, but rather in the use of supernovae by these different collaborations. Many of these collaborations, or at least the CCHP one, is from quite a bit earlier and does not use the Pantheon Plus collaboration compilation. And so there are two elements of that: the use of peculiar velocity flows, which are corrected for in Pantheon Plus, and the use of multiple supernova surveys, both on the third rung and second rung, tightened the type 1a supernova distance ladder, and together yield about a difference of 2 in the Hubble constant. So if you just combine the CCHP TRGB measurements as is to the Pantheon Plus supernovae, you'd be at about 72. Okay, I see that Radislaw is going to talk after this, so I thought I would briefly mention this asked question: is there a difference in the supernovae themselves between rungs 2 and 3? There was a pretty extensive paper by David Jones in 2018 that compared all kinds of different things. But Radislaw and Jens Hjorth claimed or saw some evidence of a difference in the relationship between supernova color and luminosity, a term we call beta, for supernovae that live on the third rung. That's where the relation is determined. So by definition, the relation is 0 here versus the second rung. And so they got a delta beta, a difference of about 1 plus or minus 0.5. So it was about, somewhere around 2 sigma. To quote their paper, there's no obvious physical basis for the difference in color corrections in the two samples. The origin would require further investigation. The thing I want to emphasize is the analysis they did was based on the supernova data that was available to us in 2016, which was a much smaller sample. And also, we only had a single light curve per supernova. Pantheon Plus is now based on multiple light curves from different sources for the same supernova. So revisiting this relation, I find about 0.4 plus or minus 0.3, about a 1.2 sigma difference. And Radislaw, we've exchanged some messages about this, confirms this. So I don't think this is anything. I also don't understand how there could be a difference. And I think it's important to distinguish things like this that are not particularly motivated, or just empirical investigations of multiple parameters, really require some high significance to be meaningful. And I don't find this one particularly so. Okay, last part of my talk: what can the James Webb Space Telescope tell us? Since I've described these complex backgrounds that we sometimes have to deal with, the clearest way to describe this is simply that JWST really removes the background. How does it do that? Through resolution. So here is a Cepheid variable shown in red that we observe through a column of stars, seen with the Hubble Space Telescope, where the blobs are bigger because Hubble has poorer resolution in the near infrared than James Webb does. So the same Cepheid seen in the same field with JWST NearCam, all the blobs get smaller, so you get a clean background where there's much less to estimate through using artificial stars. So to be clear, this is not a systematic error, because we've already used artificial stars to remove or estimate the background, but it is the largest source of scatter or statistical error in our measurement. So very, very welcome to be able to reduce this. So we have observed now 2 galaxies with the James Webb Space Telescope. The first of these is NGC 5584, which is a host of 2007 AF. This is the richest galaxy, or one of the richest galaxies in Cepheids. 225 Cepheids observed with JWST. It's at the mean distance of the Shoes host, so this is very typical. And we've observed it in 3 filters with JWST with much better resolution in the near infrared. And so I'm just showing you a small swath of Cepheids, all the ones between period of 39 days and 43 days. And what's you're supposed to really be impressed by, and you should be, because this is just blows me away, is if you look at in the H band, about 1.5, 1.6 microns, seen with the Hubble Space Telescope, the Cepheids versus the same scenes seen with the James Webb Space Telescope. The much better resolution is going to give you less scatter, because the photometry is going to be of higher precision. And so showing you what that actually looks like in practice, this is preliminary, but this is our observations in gray of the period luminosity relationship seen with HST, and in red shown with JWST. So there's a factor of 2.5 reduction in the scatter. That's pretty much what we expected because we know what the resolution of the two telescopes is, but it's outstanding to see, and it's really, tremendous work by the people who built the telescope. We see excellent agreement between the intercepts of HST and JWST. That means we're getting the same distance, and that is not unexpected. We didn't expect any difference because we're reducing the scatter. We're not changing the background. And here is for NGC 4258, which we observed just last week. And this is particularly impressive because the scatter here is down by a factor of closer to 3. And so this data just really looks outstanding. Okay, so the SHOES error budget has been coming down sort of every couple of years as we target different sources of dominant uncertainty. And we're now down to about 1.4% uncertainty. 1% is within reach, but it would be hard to do any better than that. I think the key elements coming up for us are Gaia data release 4 and 5, which will improve our calibration, and the use of JWST data. So we got time in cycle 1 and now in cycle 2 to repeat observations that HST made in something like 13 hosts of 17 supernovae, some number like that. It's a fair fraction of the sample. Okay, so my conclusions are the discrepancy is about 5 sigma. It's more or less persisted for 10 years, growing in strength. There's not a precise late universe measurement that's less than an early one, so it's pretty robust at this point. There are other methods which are generally consistent with this, though with less precision. We have gone through a pretty exhaustive study of systematics variations. We don't see any sources of internal inconsistency or excess noise, given that, in order to claim that, there's so many ways people have cut and sliced the data, you need fair significance to determine that. The tests in particular are inconsistent with some ideas that were suggested early on about dust or metallicity or crowding as explanations. JWST is really providing extraordinary data, and I'm really excited about it, and look forward to more of it coming in. So I think this Hubble tension is very interesting. Is something missing in Lambda CDM? I don't know. That's what many of you are here to talk about, but there's certainly a lot of interest in that. And I'll end there and happy to take any other questions you have.
Thank you, Adam. Do you have any questions?
So this is the same question I asked you before, and I got a strange answer to that. So Planck has some anomalies, right? CMB anomalies. And one of them is the hemispherical power asymmetry. And basically, if you split the CMB data set basically in hemispheres, you will find that H0 varies in one hemisphere over the other by something like 6 kilometers per second per megaparsec, right? And so it's sort of compelling that this is connected to the anomaly. Now, this raises the question, is there a precision below which, if you get there, that maybe you'll find that H0 actually is not so well defined. So it's more a conceptual question than anything else. If Planck basically just sets the bar and that's 1% errors or sub 1% errors, and you're motivated to get there, by whittling down your error budget, do you think H0 is going to be well defined?
I think that we've been pursuing 1% because, since Planck has precision, claims precision better than that, as a test of any cosmology, any idea that you want, it stands to reason that we're still gaining as long as we are the dominant error, and we are, and we have been, and life would get very hard for us better than 1%. I would actually quit before I would try to do better than 1% unless I had a new idea of how to do this. Just knowing what it takes to improve many of these other things. All of our uncertainties at this point are fairly equal contributors because by design we sort of address the tallest ones at each time. Now, if a new cosmological idea, some hemisphere-based thing or something comes along and says, oh, it's really important to measure, just say, for example, the Hubble constant to 1% separately in each hemisphere, if that was interesting, then we could do that. There's no reason that we couldn't do that in principle. Sometimes, and I think we've talked about this a little bit, the hemisphere thing is tricky. don't love the idea of hemispheres because it's not really hypothesis driven. It's like, what do you mean? Is it about cosmology being different in hemispheres? Then you might just be talking about supernovae, and then we should only be looking at the variation of supernovae in hemispheres, not, for example, the calibration of supernovae, which actually doesn't involve the redshift and the Hubble flow. And so, this is something I struggle with. Sometimes people try just strictly empirical things. What if I divide the data in hemispheres? And I'm usually like, which data and what is your idea of what's going on? Because it's a much more powerful test when you actually have an idea that you're proposing, and we could target the test more to the data. Otherwise, if people slice and dice the data so many ways, we lose track of what is even significant at some point. Obviously, if you check enough things, if you slice and dice enough ways, you'll find things that are 2.5 sigma, let's say, different just by chance. And so it's much more powerful, as I said, if you have a hypothesis, then you won't be just trying to check everything, and we'll know what significance means and which part of the data set to use.
Adam, just a better comment on that. So basically, the assumption in cosmology is basically the radiation dipole and the matter dipole agree. Now that's an assumption, right? So at the moment, what we're finding is an anomaly in the cosmic dipole in radio galaxies and in quasars, right? Now, if that stacks up, basically it says that H0 itself is not so well defined.
So when you say that about the radiation dipole and the matter dipole, the first thing I think is, okay, you are talking about cosmology, and you're talking about things that we only infer, let's say, from supernova data with redshifts and magnitudes. And so at that point, it's a question to ask about the Pantheon Plus data set or the supernova side of the house. And there, I would say, let's see, and you're saying then H not, I don't know. I guess if you reformulate a new cosmological model, we would look and see what role H naught plays in it, or what our measurement looks like in it. Do you have a specific scenario in mind?
No, we could just leave it there.
Okay.
Thanks.
Thank you. Any other questions?
I had a question, might be a bit of a dumb question, but you presented the delta beta values. I noticed that there was some overlap between the values with the errors. So the lowest value with delta beta. Hang on. Yeah, it's better if you show the data.
I'm looking. There, here.
Yeah. So one. It's one. No, sorry, it's the slope. Slope is the what I mean.
Beta is the slope, and so what you do here is you look at the supernova color versus the y-axis. Here is the residual. It's the supernova minus the independent distance. So in the bottom case, that is the Hubble flow or redshift itself. In the top case, that's from Cepheids. And so you're saying, where the question is there a slope in this plane?
Yeah, and if you look at the top graph,
yeah,
it's 0.4 plus or minus 0.3. So correct. At lower bound is 0.1, and the upper bound of the other one is also 0.1. Do you understand what I mean?
No. What's the question?
Well, it's if maybe this isn't exactly a discrepancy, but rather that the value is actually within the overlap of the plus or minus.
Yeah, I mean, you're saying there's not a significant difference.
No, I just mean that there is some overlap. So maybe there's maybe the actual value of the slope is there.
It's there.
There isn't a discrepancy between these two. That they do in fact match. It's just that, but only when you take into account the errors.
Yeah, I mean that's always the case, is when you take into account the errors. I mean, formally, I'm saying the difference, right? That these two numbers or measurements of this slope are independent. They use different objects, and so one could take the difference and the combined error in quadrature. And when you do that, it's 1.2 sigma is the difference. And so, you know, I don't, because people have looked at many things, you know, 1.2 sigma is not, to me, evidence of anything.
All right.
Yes.
I was wondering for the calibration of supernovae, the mass step correction.
Oh, yes, that's a great question. And you might ask that question again for Dylan, but I will say that in our shoes analysis, we do one variant, which is, I'm going to say, old school salt, which means there's a mass step in it. And so that's one variant we do, and it gets a very similar Hubble constant. For another way we do uses this more recent formalization for salt, which combines a model of how color is affected by dust for supernovae empirically, and how it is affected just intrinsically. And when you do that formulation, what was previously called the mass step actually becomes more the mass dependence of the reddening law. And as I said, Dylan could talk more about this, but it's just, it's kind of a reformulation. It gives a very similar result, but it attributes the dependence on the host galaxy, which was always small before, from being maybe supernova physics to instead maybe being dust physics.
I think we have to move on. Thanks a lot, Adam.
Sure.